Welcome to a journey that will challenge everything you thought you knew about reality. Imagine stepping into a world where the familiar rules of our universe simply cease to exist. A realm where objects can occupy multiple places simultaneously, and where the mere act of observation has the power to alter reality itself. No, we're not delving into the realm of sorcery or science fiction. We're exploring the captivating universe of quantum physics in the depths of space. What we're about to explore defies common sense and pushes the boundaries of human understanding. In this fascinating domain, particles can exist in multiple states at once, tunnel through seemingly impenetrable barriers, and communicate instantaneously across vast cosmic distances. These aren't just theoretical curiosities, they're fundamental aspects of how our universe operates at its most microscopic level. Today, we're embarking on an extraordinary expedition into one of the universe's greatest mysteries, the bizarre behavior of subatomic particles in the vacuum of space. We'll discover how these tiny entities, dancing at the edge of existence, shape everything we know about the cosmos. From the birth of stars to the evolution of galaxies, quantum mechanics plays a crucial role in orchestrating the cosmic ballet that surrounds us. Consider this: every atom in your body, every particle of light that reaches your eyes, and every bit of matter in the universe follows these strange quantum rules. Understanding these principles isn't just an academic exercise, it's the key to unlocking the deepest secrets of our universe. How do black holes really work? What happened in the first moments after the Big Bang? The answers lie in the quantum realm. If you've ever gazed at the night sky and wondered why the universe behaves so peculiarly at microscopic scales, you're about to embark on an illuminating adventure. This is your invitation to join us in unraveling the enigmatic world of quantum physics. Together, we'll explore the foundations of reality itself, venturing into a domain where the impossible becomes possible, and where our conventional understanding of the world dissolves into a sea of probability and possibility. Hit that subscribe button and turn on notifications, because this is just the beginning of our quantum journey. Each video in this series will peel back another layer of the cosmic onion, revealing the intricate dance of particles that underlies all of existence. Whether you're a seasoned physics enthusiast or simply curious about the nature of reality, this exploration of quantum mechanics in space will forever change how you view the universe around you. Let's dive into the quantum realm together, where the ordinary rules no longer apply, and where every discovery brings us closer to understanding the fundamental nature of reality itself. Welcome to the fascinating world of quantum physics in space. Our journey into quantum physics begins with one of the most revolutionary discoveries in scientific history, the dual nature of light. In the early 1800s, Thomas Young conducted his famous double-slit experiment, demonstrating that light behaves as a wave by creating interference patterns. This groundbreaking observation seemed to settle the centuries-old debate about light's nature. However, the story was far from over. Enter Albert Einstein in 1905, who turned physics on its head with his explanation of the photoelectric effect. Einstein showed that light also behaves as discrete particles, photons, that carry specific packets of energy. This seemingly contradictory nature of light, being both a wave and a particle simultaneously, became one of the cornerstones of quantum mechanics. It wasn't just a minor curiosity, it represented a fundamental truth about the nature of matter and energy at the microscopic level. The double-slit experiment took an even more bizarre turn when scientists began firing individual particles through the slits. Logic would suggest that each particle should go through one slit or the other, creating two distinct bands on the detector. Instead, something extraordinary happened. Even individual particles created an interference pattern, as if they were waves interfering with themselves. More astonishingly, this pattern emerged even when particles were fired one at a time, suggesting that each particle somehow traveled through both slits simultaneously. This leads us to one of the most profound concepts in quantum mechanics, superposition. To help visualize this mind-bending phenomenon, imagine quantum particles as dancers on an infinite stage. Unlike classical dancers who must be in one specific position at any given time, quantum dancers exist in multiple positions simultaneously, until the moment we try to observe them. It's not that we simply don't know where they are, they literally exist in multiple states at once. This strange behavior culminated in one of the most famous thought experiments in physics, Schrödinger's cat. In 1935, Erwin Schrödinger proposed a scenario where a cat in a sealed box could be simultaneously alive and dead, depending on a quantum event. This wasn't meant to be taken literally, but rather to illustrate the absurdity of applying quantum mechanical principles to everyday objects. The thought experiment highlights a fundamental question. Where exactly is the boundary between the quantum world, where objects can exist in multiple states, and our classical world, where things must be either one way or another? The implications of these quantum principles are staggering. When we observe a quantum system, we force it to choose one state from all possible states, a phenomenon known as wave function collapse. This leads to one of the most profound mysteries in physics, the measurement problem. Does consciousness play a role in collapsing quantum states? What exactly constitutes a measurement? These questions continue to puzzle physicists today. Understanding these foundational concepts is crucial because they underpin everything else in quantum mechanics. The uncertainty principle, another key concept introduced by Werner Heisenberg, tells us that we can never simultaneously know both the position and momentum of a quantum particle with perfect precision. This isn't a limitation of our measuring devices, it's a fundamental property of nature itself. Just as our quantum dancers move across their infinite stage, they follow precise mathematical rules described by the Schrödinger equation, yet their exact positions remain probabilistic until measured. This probabilistic nature of quantum mechanics challenged Einstein's deep-seated belief that God does not play dice with the universe. Yet, nearly a century of experiments has consistently confirmed these strange quantum predictions. These fundamental principles of quantum mechanics, superposition, wave-particle duality, uncertainty, and measurement, form the bedrock upon which our modern understanding of the universe is built. They're not just abstract concepts. They're the rules that govern reality at its most fundamental level, leading to technological breakthroughs like lasers, transistors, and quantum computers. As we continue our exploration of quantum physics and space, these principles will help us understand even more extraordinary phenomena, from quantum entanglement to the behavior of particles near black holes. The vast expanse of space isn't the empty void we once imagined. Instead, it's a dynamic stage where quantum mechanics performs its most spectacular shows. Even in what we call empty space, an incredible quantum dance is constantly taking place at the microscopic level. Let's begin with one of the most counterintuitive concepts in physics, the quantum vacuum. Contrary to our classical understanding, a perfect vacuum isn't empty at all. It's actually a seething ocean of virtual particles that continuously pop in and out of existence. These virtual particles appear in pairs, a particle and its antiparticle, borrowing energy from the vacuum itself for the briefest of moments before annihilating each other. This phenomenon, predicted by quantum field theory, isn't just theoretical, it has measurable effects on the real world. The Casimir effect provides tangible evidence of these vacuum fluctuations. When two parallel metal plates are placed extremely close together, they experience a tiny attractive force. This force arises because fewer virtual particles can appear between the plates than outside them, creating a pressure difference that pushes the plates together. It's as if the vacuum itself is pushing these objects toward each other, a remarkable demonstration of how quantum effects can manifest in the macroscopic world. But the influence of quantum vacuum fluctuations extends far beyond laboratory experiments. These fluctuations may play a crucial role in the expansion of the universe itself. According to some theories, the mysterious dark energy causing our universe's acceleration might be related to the energy of the quantum vacuum. As space expands, new regions of vacuum are created, each bubbling with virtual particles, potentially contributing to the universe's expansion. Perhaps even more fascinating is how quantum mechanics manifests around black holes. Near these cosmic behemoths, vacuum fluctuations take on a new significance through Hawking radiation. When virtual particle pairs appear near a black hole's event horizon, sometimes one particle falls in while the other escapes, transforming these virtual particles into real ones. This process slowly drains energy from the black hole, causing it to gradually evaporate, a process that creates a profound puzzle about information conservation in quantum mechanics. Quantum entanglement adds another layer of mystery to black holes. When particles become entangled, their quantum states become inextricably linked, regardless of the distance between them. This spooky action at a distance, as Einstein famously called it, plays a crucial role in our understanding of black hole physics. Some theorists suggest that entanglement might be the key to understanding how space and time emerge from more fundamental quantum processes. The holographic principle, inspired by black hole physics, suggests that all the information contained in a volume of space can be encoded on its boundary, much like a hologram. This mind-bending concept implies that our three-dimensional reality might be an illusion, emerging from information stored on a two-dimensional surface. This principle has profound implications for our understanding of space, time, and the nature of reality itself. These quantum phenomena in space raise profound questions about the fabric of reality. How do quantum effects influence the large-scale structure of the universe? Could quantum mechanics hold the key to unifying gravity with the other fundamental forces? What role does quantum entanglement play in the cosmic web that connects all matter? What fascinates you most about these quantum phenomena? Is it the mysterious virtual particles popping in and out of existence? The mind-bending implications of quantum entanglement? Or perhaps the role of quantum mechanics in black hole physics? Share your thoughts in the comments below. Your curiosity might just inspire our next deep dive into the quantum realm. Remember, every question you ask brings us one step closer to understanding the quantum nature of our universe. The space around us holds countless mysteries waiting to be unraveled, and together, we're pushing the boundaries of human knowledge into the quantum frontier. As we delve deeper into the quantum realm, we encounter mysteries that challenge not just our understanding of physics, but the very nature of reality itself. Let's explore some of the most profound questions that lie at the intersection of quantum mechanics and cosmology. Stephen Hawking's groundbreaking work on black hole radiation opened up an entirely new realm of quantum puzzles. Hawking radiation suggests that black holes slowly evaporate by emitting particles, but this creates a paradox. What happens to the information about everything that fell into the black hole? According to quantum mechanics, information cannot be destroyed, yet black holes seem to violate this principle. This is known as the black hole information paradox, and it represents one of the greatest challenges in modern physics. When a quantum system falls into a black hole, its information becomes scrambled in a way we don't fully understand. Some theorists propose that the information might be encoded on the black hole's event horizon, like a hologram. Others suggest it might escape through subtle correlations in the Hawking radiation. The resolution to this paradox could reveal fundamental truths about how space, time, and information are connected at the quantum level. The measurement problem takes on cosmic proportions when we consider the universe as a quantum system. In laboratory experiments, we say that quantum systems remain in superposition until measured by an observer. But what happens when we apply this to the entire universe? Who or what plays the role of the observer? This leads to profound questions about consciousness, reality, and the role of observation in quantum mechanics. This cosmic measurement problem has led to various interpretations of quantum mechanics. The Copenhagen interpretation suggests that measurement causes wave function collapse, but doesn't explain what constitutes a measurement. The many worlds interpretation takes a more radical approach, proposing that every possible quantum outcome actually occurs in different, branching universes. Speaking of multiple universes, quantum mechanics has given rise to several theories about parallel realities. The concept of quantum decoherence suggests that when quantum systems interact with their environment, they gradually lose their quantum properties and begin to appear more classical. This might explain why we don't see quantum superpositions in everyday objects, but it also hints at the possibility of quantum worlds beyond our classical reality. The many worlds interpretation proposed by Hugh Everett III suggests that every quantum possibility is realized in some universe. When a quantum measurement is made, instead of the wave function collapsing, the universe splits into multiple branches, each containing a different outcome. While this might sound like science fiction, it's a serious scientific theory that attempts to resolve some of the deepest paradoxes in quantum mechanics. If particles can exist in multiple states simultaneously, could multiple versions of our universe exist? This isn't just a philosophical question. It has profound implications for our understanding of reality. The mathematics of quantum mechanics suggests that quantum superposition applies to everything, from single particles to entire universes. Could our universe be just one branch in an infinite tree of possible realities? Recent developments in quantum computing have begun to shed new light on these questions. Quantum computers manipulate quantum states directly, allowing us to explore how quantum information behaves in controlled environments. These experiments might eventually help us understand how quantum information is preserved or lost in extreme conditions like those near black holes. The quantum entanglement of black holes has led to another fascinating discovery. quantum error correction seems to be built into the fabric of space-time itself. This suggests that the universe might have natural mechanisms for preserving quantum information, even in extreme conditions. Some theorists propose that this might be the key to resolving the black hole information paradox. These mysteries point to a deeper truth. Our universe might be fundamentally quantum in nature, with classical reality emerging as a kind of approximation. The quest to understand these quantum mysteries isn't just about solving abstract puzzles. It's about understanding the very nature of reality itself. As we continue to explore these questions, new experimental techniques and theoretical insights are pushing the boundaries of our understanding. From quantum telescopes that might detect dark matter to experiments testing quantum mechanics at increasingly large scales, we're gradually unveiling the quantum nature of our universe. The journey to understand these mysteries continues, and each answer seems to reveal new questions. Perhaps that's the true beauty of quantum mechanics. It reminds us that the universe is far more mysterious and interconnected than we ever imagined. Take a moment to pause and truly contemplate this mind-bending question. We've learned that at the quantum level, particles can exist in multiple states at once, a phenomenon called quantum superposition. But what if we extend this principle to its logical, albeit extraordinary, conclusion? What if our entire universe could exist in multiple states simultaneously? Consider this. Every quantum event in our universe presents multiple possibilities. When we measure these events, we observe only one outcome, but quantum mechanics suggests that all possible outcomes might actually occur. At first glance, this might seem relevant only at the microscopic scale. However, our universe is ultimately built from these quantum building blocks. If each quantum particle can exist in multiple states, couldn't larger systems, including the universe itself, potentially exist in multiple versions? This is where the many worlds interpretation of quantum mechanics, proposed by Hugh Everett III, becomes particularly intriguing. According to this interpretation, every time a quantum event occurs, the universe splits into multiple branches, each representing a different possible outcome. In one branch, the particle spins up, in another it spins down. In one branch, you decided to read this article today. In another, you made a different choice. Think about the profound implications of this idea. Every decision you've ever made, every quantum fluctuation since the Big Bang, every possible arrangement of particles, all might exist simultaneously in different branches of a vast, ever-expanding multiverse. These branches aren't parallel universes in some distant space. They're different versions of our universe, existing in a higher dimensional space that we can't directly observe. But this raises fascinating questions. If multiple versions of our universe exist, why do we only experience one version? Are these other versions truly real, in the same way our experienced reality is real? Could there be a way to detect or even communicate with these other branches? Some scientists propose that quantum computers might eventually help us explore these questions. By maintaining large-scale quantum superpositions, quantum computers could potentially give us insights into how quantum mechanics operates at larger scales. While we can't directly observe other universe branches, we might be able to detect subtle hints of their existence through carefully designed experiments. The implications extend beyond pure physics. If multiple versions of our universe exist, what does this mean for concepts like free will, consciousness, and the nature of reality itself? Are all possible versions of you equally real? Does consciousness play a role in selecting which branch of the universe we experience? These questions aren't just philosophical musings. They're at the heart of our understanding of quantum mechanics and the nature of reality. While we may not have definitive answers yet, the very fact that quantum mechanics leads us to such profound questions highlights the extraordinary nature of our universe. So, the next time you make a decision, consider this. Perhaps in another branch of the quantum multiverse, you made a different choice. Perhaps there are countless versions of you, living out all the possibilities that quantum mechanics allows. It's a humbling thought that reminds us just how mysterious and magnificent our quantum universe truly is. What do you think? Could multiple versions of our universe truly exist? How would your perspective on life change if you knew for certain that every possible version of reality was playing out somewhere in the quantum multiverse? Take a moment to ponder these questions and let them expand your understanding of what might be possible in our quantum reality. Remember, even if we can't definitively prove the existence of multiple universes, the fact that quantum mechanics allows for such possibilities shows us that reality is far more fascinating and complex than our everyday experiences suggest. Quantum technologies are revolutionizing our approach to space exploration, offering unprecedented capabilities that seem to leap straight from science fiction into reality. Let's explore how these quantum advances are shaping our cosmic future. Quantum computing stands at the forefront of this revolution. Unlike classical computers, which process bits in either 0 or 1 states, quantum computers utilize qubits that can exist in multiple states simultaneously. This quantum advantage could transform space exploration in several groundbreaking ways. For instance, quantum computers could optimize spacecraft trajectories by calculating countless possible paths simultaneously, finding the most efficient routes through complex gravitational fields. They could also simulate advanced materials for spacecraft, predicting their behavior under extreme conditions with unprecedented accuracy. The potential of quantum computing in space weather prediction is particularly exciting. These advanced systems could process vast amounts of data about solar activity, magnetic field interactions, and particle behavior, enabling us to protect both astronauts and satellites from dangerous solar events with far greater precision than ever before. Imagine being able to predict solar flares and coronal mass ejections with the same accuracy we now predict Earth's weather. Quantum communication represents another frontier that could revolutionize space exploration. Through quantum entanglement, we can create unhackable communication channels between Earth and space missions. China has already demonstrated this potential with their Mischius satellite, successfully conducting quantum-encrypted communications across thousands of kilometers. This technology could ensure absolutely secure communication channels for future deep space missions. The concept of quantum teleportation, the ability to transmit quantum states across space, could transform how we send information through the cosmos. While this doesn't mean teleporting physical objects Star Trek style, it could allow for instantaneous transmission of quantum information across vast distances, potentially revolutionizing deep space communication. Perhaps one of the most promising applications lies in quantum navigation. Future spacecraft might use quantum sensors to detect minute gravitational fields, enabling precise navigation without relying on signals from Earth. These quantum accelerometers and gyroscopes could measure movement and position with incredible accuracy, allowing spacecraft to navigate autonomously through the solar system and beyond. Quantum clock synchronization presents another fascinating possibility. Using entangled particles, we could maintain perfectly synchronized time across vast distances in space, crucial for future interplanetary missions and space-based networks. This quantum-enhanced precision would far exceed our current atomic clock capabilities. Looking further into the future, quantum technologies might enable even more ambitious projects. Imagine quantum radar systems that could detect dark matter, or quantum sensors capable of identifying habitable exoplanets with unprecedented detail. Quantum-based propulsion systems, though still theoretical, could potentially achieve efficiencies far beyond our current chemical rockets. The development of space-based quantum networks could form the backbone of a future quantum internet, extending throughout our solar system. This network could connect quantum computers on different planets, creating an interplanetary quantum computing grid with enormous processing power. However, significant challenges remain. Quantum systems are notoriously sensitive to environmental interference, and space presents harsh conditions. Scientists are working on making quantum technologies more robust and developing error correction methods that could maintain quantum states in space environments. The integration of artificial intelligence with quantum systems presents particularly exciting possibilities. Quantum-enhanced AI could manage complex space operations, make split-second decisions during critical missions, and process vast amounts of astronomical data to identify patterns beyond human recognition capabilities. Testing quantum physics in space also offers unique opportunities to explore fundamental questions about the nature of reality. The extreme conditions and vast distances of space provide natural laboratories for testing quantum theories at scales impossible to achieve on Earth. As we stand on the brink of this quantum space age, one thing is clear. The marriage of quantum physics and space exploration will open doors we've only dreamed of. From securing our communications to navigating the cosmos, quantum technologies are not just enhancing our current capabilities, they're fundamentally changing what we believe is possible in space exploration. The future of space exploration looks increasingly quantum, promising discoveries and capabilities that could transform our understanding of the universe and our place within it. As these technologies mature, we may find ourselves capable of achievements that today seem like pure science fiction. As we reach the end of our journey through the quantum realm, we find ourselves standing at the edge of human understanding, gazing into an abyss of possibilities that challenges everything we thought we knew about reality. The quantum world has shown us that the universe is far more extraordinary, more mysterious, and more interconnected than we ever imagined. Throughout this exploration, we've witnessed how quantum physics defies our common-sense expectations. We've seen particles exist in multiple places simultaneously, encountered the strange dance of quantum entanglement, and pondered the possibility of multiple universes. Each discovery peels back another layer of cosmic mystery, only to reveal even more profound questions lying beneath. What we've learned is both humbling and inspiring. Humbling, because it shows us how much we still don't understand about the fundamental nature of reality. Inspiring, because each new discovery opens doors to technological advances that could transform our future in space exploration and beyond. From quantum computers that could unlock the secrets of dark matter to entangled communication networks spanning the solar system, we stand on the brink of a new era in human achievement. Yet perhaps the most profound lesson from quantum physics is that reality itself is far stranger and more magnificent than our human minds evolved to comprehend. The fact that particles can influence each other instantaneously across vast distances, that empty space is actually teeming with virtual particles, and that observation itself plays a crucial role in determining reality. These insights suggest that we're just beginning to glimpse the true nature of our universe. Every question we've answered has led to new mysteries. Every solution has unveiled new puzzles. And that's exactly what makes this field so exciting. We're not just passive observers of the cosmos. We're active participants in the greatest scientific adventure humanity has ever undertaken: the quest to understand the fundamental nature of reality itself. Here at Exploring the Universe, we're committed to continuing this journey of discovery with you. Each video is another step into the unknown, another piece of the cosmic puzzle, another moment of wonder shared with our community of curious minds. The questions we explore together, about quantum mechanics, about the nature of reality, about our place in this vast quantum universe, these are the questions that push the boundaries of human knowledge and imagination. If you've been fascinated by this journey through the quantum realm, if you found yourself wondering about the deeper nature of reality, if you felt that spark of curiosity ignite within you, then you're already part of this grand adventure. Don't keep these mysteries to yourself. Share this video with friends who share your fascination with the unknown. Subscribe to join us on future explorations and become part of a community dedicated to unraveling the deepest mysteries of the cosmos. Remember, every great discovery in science began with a simple question, a moment of curiosity, a willingness to explore the unknown. Together, we're not just learning about the universe, we're participating in humanity's greatest quest for understanding. The quantum realm awaits, with all its mysteries and marvels, and our journey is just beginning. Thank you for joining us on this exploration of quantum physics and the cosmos. Until next time, keep questioning, keep exploring, and keep wondering about the extraordinary quantum universe we call home. The greatest mysteries of the cosmos are still waiting to be discovered, and together, we'll continue pushing the boundaries of human knowledge into the quantum frontier.